This is our video for day 11, unit 6. So the last two videos we've gone over all the transformations applied to sine and cosine function. In the last video we did the tangent function. Today we're going to do is take those ideas with the transformations and actually use them to model situations, use them for modeling purposes. So we use sine and cosine for is modeling data we call periodic data. So this is data that repeats at regular intervals. So this kind of function used to model any kind of data that repeats at regular intervals. Some common applications we'll use in class, you'll see on your examples. In the practice set tomorrow is things like tides, ocean tides, weather, temperature, human heartbeat will be one example of that in this video. And other things like that that repeat regularly at a set interval. So working through these problems the same way as we worked through transformations. So we're trying to think about all our transformations. We have our sine and cosine functions. I have A sine, had our frequency, our phase shift, and our vertical shift, which is our midline. Right, and that can work for sine or cosine also, so we use both. So the only thing that are changing in each one of these is our values for A, the vertical stretch, which is going to be the amplitude. The value for B, the frequency, our phase shift, H, and vertical shift, K, which will be the midline of the function. So when we read through the problem, that's what we're looking for, things that give us amplitude, frequency, phase shift, vertical shift. Alright, so we're going to go back and forth between these two slides as we go through this. So first thing we're going to look for is try and identify what the period is. So if we go back, look at this problem we see is talking about a human heartbeat. We have blood pressure is systolic blood pressure over diastolic blood pressure. So it tells good target blood pressure is below 120/80. We're trying to model this. And the last sentence is what gives us the period. So we have a heart rate of 80 beats per minute. So that's the piece that's going to be the key for our period. Right? We know the rate is going to be 80 beats per 1 minute or 60 seconds. Alright, so for each heartbeat, that's 1 1/3 heartbeats per second. Or we can use a fraction, say 4/3. So this right here is our period. This is one full cycle. What we're trying to model is a heartbeat. This is the amount of time that takes, 4/3 of a second, 1 1/3 seconds. The period itself is not what goes into our function. What goes into the function is frequency. So to find the frequency, if we're using degrees, the frequency is 360, which is the period of the parent function, divided by period. So here that would be 360 divided by 4/3, which would be 270. This would be my B value in terms of transformations on the function. Most of the problems we'll work with in class are going to be not in degrees, but in radians. So the formula is still the same, except we use the radian period for the parent function, which is 2 pi. And And so that will give us a frequency of 3 pi over 2. Right, and that's our b value that will put into the function. We'll work through this one in both degrees and radians, and then the next one we'll do with just radians. So there we have our frequency. That's the first piece we need to put in to our function. The next thing we're going to look for is amplitude. So before we go back and look for amplitude, remember our formula we have for amplitude and midline are very similar. They both involve the maximum and the minimum. So the amplitude is half the distance between the maximum and the minimum, and the midline is the average of the maximum and the minimum. So amplitude is half the difference, and midline is half the sum. So we're going to go back, see if we can find some numbers that indicate our maximum and our minimum, and then we'll be able to find both the amplitude and the midline from that. So again, we're trying to model the blood pressure to look for where do we have a maximum blood pressure. Right, so we look at this sentence here, it tells us systolic blood pressure is the pressure when your heart beats, that's the higher one, over diastolic, which is the pressure when your heart rests, that's the lower one. Right, and it tells us here we're looking for 120 over 80. So it tells us 120 is going to be our max, right, our systolic blood pressure, and 80 will be our minimum, our diastolic blood pressure. So using those as max and min, we can go back and find both the amplitude and the midline. So for amplitude, it's going to be 120 minus 80 over 2. So that'll be 40 divided by 2, or 20 will be our amplitude. And that's what we'll put in for A in our function in terms of our transformations. Same idea for the midline, max is 120. This time we're adding 80, we're taking the average of 120 and 80. Right, together that makes 200, and divided by 2 will be 100. That's going to be our midline. Right, midline, same thing as our vertical shift, or K in terms of our transformations. So the next piece is, are we going to use a sine or a cosine function? So the way we decide that is we look at where the function starts. Where is the function at 0? We use cosine if it's at an extreme at 0. So if it's at a maximum or a minimum at 0, we're going to use cosine. If it's at an average value at 0, we're going to use sine. So for this one, we're just modeling the heartbeat, so we don't need to overcomplicate this. We can start when the heart beats and then go through one full cycle. So start at the maximum, which means we're going to use cosine for this one. Right, we're going to use cosine because we're going to start at the maximum. Right, and the last piece, and the hardest piece, is the phase shift. For this one, there is no phase shift. We just decided we're going to start at our maximum. If there is a phase shift, again, remember the way we have to write the function and rewrite it using our frequency factored out from the x. So on this one, there's no phase shift. Because we're starting at our maximum, and cosine already starts at a maximum, so we don't need to move it left to right to line it up. So putting all these pieces together here, we can plug in and come up with this function. So we'll say pressure in terms of time equals 20, which is our amplitude. Cosine, because it starts at a maximum. Our frequency using degrees was 270. T, and then our midline was 100. Right, or we can do the same thing for radians. The only difference there is our frequency won't be 270 anymore, right? It has 3 pi over 2. Right, and then graphing it is the same as we went over in the video from day 9. So we just look at each piece of the function to figure out how we're going to graph it. So first thing is we see the midline is 100, so this middle line here is going to represent 100 on the y-axis. All right, and I use the amplitude above and below that to mark off the maximum and minimum. Let's go up to 120 and down to 80. So along the x-axis, I'm marking off the length of one period. I'm making a special point following the pattern every 1/4 of the way through the period. So on the previous page, we said that the period is 1 1/3 um, seconds. That's how long it takes. So it's going to be 4/3, 1, 2/3, and 1/3. So every quarter of the way will be 1/3 of a second. Right, once everything's marked off, we're just going to follow our pattern for the cosine function. So it's max, 0, min, 0, max. So here's our function. We have two functions, 1 degree, 1 radian, and our graph to model the heartbeat, the blood pressure while the heart beats. So I'm going to go through the same process, same idea for the second example. All right, we're going to go through and try and find each of these pieces of the function. All right, I need to find A, our amplitude, our vertical stretch, B, the frequency, phase shift if there is one, and midline. So again, just like the last one, the first thing we're going to look for is the period. So we're looking for how long it takes one full cycle to occur. So we look, this problem here is about ocean tide, so high tide and low tide. All right, so in this case, high tide would represent the maximum, and low tide would represent the minimum. Right, so whether it's sine or cosine, if we go from the minimum to the maximum, that's going to be half the period. So if we're going from 4 a.m. to 10 a.m., right, that's 6 hours, is 1/2 of the period. So the full period is going to be 12 hours. So go back on the next page. We know our period is going to be 12 hours. And we can use that to find the frequency. Right, the frequency is what we'll actually put into the rule of the function. So our frequency is going to be 2 pi over the period. So that's 2 pi over 12, right, which we can simplify pi over 6. So there's one piece of the function. So next thing we'll look for is amplitude. Remember, for amplitude, we're using a formula that involves the same pieces as a formula for the midline. Right, it's going to be max minus min over 2 for amplitude. Half the difference for midline is half the sum. Max plus min over 2. So now we need to go through and see if we can find numbers that tell us our maximum and minimum. Right, and here we have 13 feet at high tide, 5 feet at low tide. So that one should jump out at you. You have your maximum and your minimum right there. So we go back to our formula. We put 13 in for the maximum. Put 5 in for the minimum. 13 minus 5 will give us 8. Divided by 2 will give us 4. So this will be the amplitude for the function. My vertical stretch, we'll do the same thing here, finding the midline. Maximum will be 13, minimum 5. We're going to add them together. Taking the average, that's 18 over 2, and that's going to be 9. Right, so that's going to be k when I write my function. So next thing we're going to look at is whether we're going to use a sine or a cosine function. This one's a little tricky. If we look at the way the problem's written, it says we're writing a function to model the height of the water over the course of a day, right? Which means starting from 0 corresponding to midnight. So we're not starting at a maximum, we're not starting at a minimum, we're starting somewhere in between, so we're going to use sine. Right, so pretty much anytime we're not explicitly starting at a max or minimum, we'll use sine. So the last piece is the phase shift. This is the piece that's the most tricky to figure out. So to understand the phase shift, we want to think about our pattern for sine. We start with 0, go up to a max, back to 0, down to a min, and then back up to 0. That's our usual pattern. Remember, each point happens 1/4 of the way through the period. So what we know from this problem is that our minimum is occurring at 4 a.m. So we're shifting this function so that this minimum point is happening at 4 a.m., which is 1/3 of the way through the period. So that's basically where we're starting. We're shifting to get our minimum 1/3 of the way through the period, which means I have to shift this minimum back to the left. So now when you think about what 1/3 of the way through the period is. So 4 hours is 1/3 of the way through the period. Where should the regular minimum be happening? If this was starting at 0, right, it would be 0, 3, 6, 9, and then 12, right? Every jump would be 1/4 of the way, which would be 3 hours, right? So the minimum should be happening at 9. Instead, it's happening at 4. So we shifted it left 5. We moved it left by 5 hours. Right, so means you write it in that form, our phase shift, our h value, we're going to have a +5, shifting it left 5. So what we're trying to do with the phase shift is get the correct pieces to line up, see where they should go and where they are, and what we have to do to shift them there. So we look at where the minimum currently is, where it would be on a regular sine function, and see how we can move that function to line it up. So putting everything together, we'll have our model on the next page. We'll have here it's h, t, height of the water, and we'll go put all the pieces in. So we know our amplitude was 4, so it'll be 4, we're using a sine function. Have our frequency of pi over 6. Remember, that's factored out, x plus 5 to shift that phase shift left 5, and then our midline of 9. So this is something that will take some practice. We'll work through several practice problems in class tomorrow and do a more in-depth example on Wednesday in class. So again, we want to graph this. You know the 9 is our midline right here. We're going up and down 4 from there, so up to a maximum of 13, down to a minimum of 5. So we want to mark off, we know we're starting from 4, we're starting at that minimum at 4, and the period is 12. So that means we're going out to 16. Make sure we get one full period. We're going to have a mark every quarter of the way, and 1/4 of 12 is 3. So every jump on these is going to be 3. So 7, 10, 13. From here, we're just going to follow the 5-point pattern. Remember that we're starting at a minimum. So we get to the minimum, we go up to 0, up to the maximum, back down to the 0, and back down to the minimum. Right, and the last thing we're going to do is look back at the question, make sure we're answering the question, because it asks us to write it over the course of a day. So we need to write this to extend to go at least 24 hours. So if we go back, we can go back 1. Again, we're always jumping by 1/4 of the period, so that's going to be 3 here. So this will be 1 over here. Keep moving out. 3 here would be 19. And 22. And then 25, and I'll be through a full day. So we just keep following that same pattern. So we go from 0 down to the minimum at 4, to the 0 at 7, maximum at 10, 0 at 13, minimum 16, 0 19, maximum at 22, and then back down to 0 at 25. And that will give us a full day. So that's it for this video. It's just those 2 examples. If you want to see some more examples, you can look up videos on YouTube modeling with sine functions. There should be a lot of videos of things like that on YouTube. It's a very common topic you see in pre-calculus and AFM classes, so there should be a lot of resources available if you look for them.